this is Swathi, working as Assistant Professor in the Department of Electronics and Communication Engineering in Institute of Aeronautical Engineering, Dundigal. Welcome to this lecture. In this lecture, we'll be discussing some questions from the tutorial question bank, which is uploaded in the IARE website. And I want to discuss the question bank on Module 5, that is Sequential Circuit Fundamentals. So while discussing the theory and problems, we have discussed what do you mean by sequential circuit, what are the various types of sequential circuits, what is a basic building block, that is a flip-flop, different types of flip-flops, the conversion between one flip-flop to the other flip-flop. Before that, we have seen what is excitation table, how to get the excitation table of various flip-flops, and what are the characteristic tables and equations of all the types of flip-flops, and their advantages and drawbacks. So, and also how the flip-flops are used in the designing of synchronous and asynchronous sequential circuits like counters and registers. And we have also seen some problems on synchronous, that is sequential, synchronous counters and asynchronous counters. So these are all the topics that were covered in Module 5. So we will be discussing how the questions are being asked from Module 5, that is on Sequential Circuits Fundamentals. So now let us start our discussion with Part A, that is Problem Solving and Critical Thinking Questions. So the first question in that is, explain the working of 3-bit asynchronous up-down counter with necessary waveforms and truth table. First of all, when this question is asked, first we need to write down what is an asynchronous counter. So why it is so called? So any counter is constructed by cascading number of flip-flops. So while cascading the flip-flops, if all the flip-flops are applied with same clock, then that type of counter is said to be synchronous counter. If all the flip-flops are applied with different clocks, like the first flip-flop is applied with the clock pulse whose pulses are to be counted, whereas the second flip-flop is applied with the output of first flip-flop is applied as clock input to the second flip-flop, and the second flip-flop output is applied as clock input to the third flip-flop. So like that, if all the flip-flops are applied with a different clock, then we are calling that type of counter. Not only counter, any sequential circuits, in that if all the flip-flops are not applied with the same clock, that means each flip-flop is operating with different clock pulses, then such type of counters are said to be asynchronous counter or else asynchronous sequential circuit. So first write down the statement of definition of asynchronous counter, and the definition should be this way. So if all the flip-flops in the counter are applied with different clocks, or else all the flip-flops are working with the different clocks, then we call that counter as a asynchronous counter. Then 3-bit asynchronous counter. For constructing a 3-bit asynchronous counter, we require 3 flip-flops. So because as it has three bits, and each flip-flop is capable of storing only 1 bit of information. So as I want to implement a 3-bit counter, I require 3 flip-flops. So just mention that point and draw the logic circuit of 3-bit asynchronous counter. So this is the logic circuit of 3-bit asynchronous up-down counter. So that means, what do you mean by up-down counter? You have to mention that point also. The counter which can perform up counting as well as the down counting, or else the counter which can count in the incremental and decremental order. Such type of counter is said to be up or down counter. So this is the counter, the up-down counter. So where we have 3 types of 3 flip-flops here. Those are of JK type. So JK flip-flop 1, 2, 3. And along with the flip-flops, in order to drive the clock of the other flip-flop, we have some AOI logic. So this is the AOI logic. So which is giving the in clock input to the flip-flop here. So whereas just explain few points about the operation here. So the control input we have here is up or down control input, where it decides whether the counting is done in the incremental mode or else in the decremental mode. So depending on the control input, the counter can count in the incremental order or else in the decremental order. If this up or down count value is equals to 1, then what happens? One thing we have to remember, so the counter performs up counting operation when the Q output of the flip flop is one flip flop is given as clock input to the next flip flop. That is up counting. If Q bar is connected as clock to the next flip flop, then it performs the down counting. So depending on up or down control input, either Q or Q bar will be connected as input to the other flip flop, and hence it can perform the up or down counting. So this is the up or down that is 3-bit asynchronous up down counter. So where it can perform or else where it can count the pulses in incremental order as well as the decremental order. So just mention some few points about the operation of this one, and then draw the timing diagram. So here here the control input is 1, logic 1 means what it is doing? It is performing, this is MSB and this is LSB. It is performing up counting operation. If this is 0, then it could perform, if the control input is 0, it could perform the down counting operation. So that is how you have to answer this question. So next, design a synchronous counter using JK flip flop to count the following sequence 0, 2, 5, 6, 0. Undesired states, those are 1, 3, 4, 7 must go to 0 on the next clock pulse. So what should we do? We should design a counter circuit which can count the pulses in the order 0, 2, 5, 6, 0. So that means once the 0 has happened, then during the next clock pulse, the count has to become 2. And during the next clock pulse, it has to go to 5. It has to go to, these are all the states of the counter which has to be undergone. So now what is the, first of all, we need to recall the process of designing synchronous counter. So what is this, what is that? So first of all, we need to draw the table here. So that is state table. So here we have, in the state table, we have present state. So let us indicate that as, so what is the maximum state we have? 6. So that is 7. So means in order to count 7 pulses, how many flip-flops are required here? 3. So that is why I can take that as QA, QB, QC. This is the present state. And next state I am representing it as QA plus, QB plus and QC plus. Right? So now what I have to do? Now, first of all, what is the first initial state? I have to consider 0. If the present state is 0, now I am applying the clock pulse here. So let us consider raising edge of the clock pulse. So for every raising edge of the clock pulse, if the present state is 0, the next state it has to go back to 0, 1, 0. If the present state is 0, 1, 0 and I have applied a clock pulse, then the next state should be 5, where the 5 in binary can be represented as 1, 0, 1. So first of all, we need to draw a diagram. So what is that? Mentioning the state diagram. From 0 it has to go to 2. From 2 it has to go to 5. From 5 it has to go to 6. And from 6 again it has to go back to 0. 0, 2, 5, 6, 0. Right? Whereas 1, 3, 4, 7 are considered to be not specified condition. That means these are undesired states, and whenever these states happen, so then whenever the present state is this one, the next state will be obviously 0 as it is mentioned in the problem here. Now 1, 0, 1. If my present state is 1, 0, 1, the next state should be 1, 1, 0. If my present state is 1, 1, 0, next state should be 0, 0, 0 again. If my present state is 0, 0, 1, then next state should be 0, 0, 0. If my present state is 0, 1, 1, then next state should be 0, 0. That means by default, if my present state is 0, 0, 1, I am applying a clock, then it should go back to 0 state. Next, similarly, 1, 0, 0, if my present state is 0, 1, 0, 0, next state is also considered to be 0. 1, 1, 1, it is also considered to be 0. So this is a truth table, right? So or else a state table, which is representing the next state of the counter by considering the present state value, right? So now as he has mentioned that once a table has been prepared, we need to identify the proper flip-flop. So as it is already mentioned, we need to implement this or else design this counter using JK flip-flop. Now take the JK flip-flop excitation table and consider and implement the Boolean function for next state in terms of present state. Next state in terms of present state, and then derive the simplified Boolean expression for all this QA plus QB plus QC plus using K-map, and then finally you implement the logic circuit using the flip-flops. Okay, so this is the procedure. First, what we need to do, we need to identify the state diagram, and then from that state diagram we need to implement the state table, which is listing the present state as well as the next state. Okay, and finally we have to get the next state Boolean function in terms of present state, and finally implement it using the required flip-flop here. What is the required flip-flop here? It is JK flip-flop, and it is mentioned that it is a synchronous counter. So what should we remember? In case of synchronous counter, all the 3 JK flip-flops should be applied with same clock. So what we have to do? We have to take 3 JK flip-flops. Okay, so J, let us consider JA, KA, JB, KB and JC, KC, right? So we need to apply all the flip-flops with the same clock. So this is what synchronization or a synchronous clock pulse. This is clock pulse, right? And based on the equations we are getting here, I have to derive the input equations so that I will be getting. That means what we need to do, we need to again draw the table which is showing the with respect to that is we need to implement conversion table, and then we have to implement the Boolean functions for QA plus QB plus QC plus in terms of present state as well as the input JA, KA, KB, that is the inputs of flip-flops, and then draw the logic circuit. Okay, so you can go through the problem video lecture, that is problems on synchronous counter, if you have any doubt in how the designing of synchronous counter. I am just giving you the idea, so if you have any doubt, you can just go through that video. Now construct a 4-bit binary counter using D flip-flops which counts all possible odd numbers only. Which counts all possible odd numbers only means what? Here, now initially, that means first of all we have to identify the state diagram. So what it is given? It is a 4-bit counter. Totally how many pulses it can count? By using a 4-bit counter, I can count 0 to 15. That means 16 pulses I can count. 16 pulses I can count. But what he has asked, which counts all possible odd numbers only. All possible odd numbers means 1, 3, 5, 7, 9, 11, 13, 15. And remaining all are considered to be 0, right? So that is why when the present state and next state I am taking, as it is a 4-bit counter, QA, QB, QC, QD we need to take, and next state as QA plus, QB plus, QC plus, QD plus, right? So now it has to count only odd numbers, right? 0, 0. Let us consider my present state is 0, 0, 1. So the next state will be 0, 0, 1, 1 because after 1. So that means if my present state is 1, then it will go to 3. If my present state is 3, it will go to 5. If my present state is 7, then it will go to 9. Okay, so it is going to 9. And then if my present state is 9, the next state will be 11. If my present state is 11, next state will be 13. And if my present state is 15, next state should be 1. So meanwhile, if you have any even states, for all the even numbers like 2, 0, 2, 4, 6, 8, 10, next 12, 14, we have to consider the next state as 0. Next state as 0. So now if my present state is 0, 1, 1, then it has to go to 0, 1, 0. 0, 1, 0, 1. Next, if my present state is 0, 1, 0, 1, next state will be 0, 1, 1. Next, if my present state is 7, then next state will be 9. That is 1001. If my present state is 10101, the next state will be 1011. If 1011, then the next state 1101. Next, if it is 1101, the next state will be 111. So this is the present state and next state. If my present state is any one of these values or else these combinations, then next state should be considered as 0. Okay, and then take the D flip-flop excitation table. I hope you know the excitation table, and then write down the characteristic table for this 4-bit binary counter, which can count only odd numbers, and from that you can derive the expression, simplified Boolean expressions for QA plus QB plus QC plus QD plus in terms of QA, QB, QC, QD and flip-flop inputs, that is D flip-flop inputs, and then implement the binary counter using D flip-flop. That means after getting the Boolean function, just draw the logic circuit using that. Now, develop a modular 12 synchronous up counter. Modular 12 synchronous up counter using T flip-flop and draw the circuit diagram. Modular 12. Modular 12 means it can count 12 pulses. It can count 12 pulses. To count the 12 pulses, what is the minimum number of flip-flops required? So, that is 4. 4 flip-flops are required. So, it has to count only 12 pulses. What about the other remaining? By using 4 flip-flops, I can design a 16-bit counter. But it has to count only 12 pulses. Whereas the remaining 4 are all considered to be don't cares. Remaining 4 are all considered to be don't cares. Now, if you consider the truth table, just I'm giving you the idea, you can just go through that procedure. So, the present state, so again QA, QB, QC, QD. Next state value is, so we can write it as QA plus, QB plus, QC plus and QD plus, right? So, it can count up to 12 pulses, that is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Whereas, the remaining pulses, that is 12, 13, 14, 15 are considered to be don't cares. That means if these happen, if these are the present states, then the next state values are considered to be don't cares. So for this also 1100, it also the next state is considered to be don't care. As it is not mentioned, what is the output that we have to consider for the remaining combinations. So that is why we are taking it as don't care. And if it is 000, the next state will be 0001. If my present state is 0001, next state, it has to go to state 2. That means it has to count to 0010. So like that. Okay. So if my present state is 1010, next state will be 1011. If my state is 1011, the next state it has to go back to 0 again. So 0. So by considering the don't cares, we need to draw the K-map and we have to get the expression for QA plus, QB plus, QC plus, QD plus, and by using the Boolean functions, that is simplified Boolean expression, you can implement the 12-bit modular 12 counter, synchronous up counter using T flip-flops. For this, we need to get the truth excitation table of T flip-flop, and then we have to derive the characteristic table for the modular 12 synchronous up counter. Now, the next topic is how do you convert a JK flip-flop into D flip-flop? How to convert a JK flip-flop into D flip-flop? So, first of all, we have a conversion process for converting one form of flip-flop into other type. So, what is the procedure? Just we have a look at this. Write the truth table of the desired flip-flop. So, what is the desired flip-flop here? D flip-flop. So, we need to write the truth table of D flip-flop and obtain the excitation table for the given flip-flop. What is the given flip-flop? JK flip-flop. So, get the excitation table of JK flip-flop. Append the excitation table of given flip-flop and truth table of desired flip-flop appropriately to obtain the conversion table. So, by using both of these, we need to obtain the conversion table. And simplify the expression for the inputs of the given flip-flop in terms of desired flip-flop and also the outputs, and design the necessary circuit and make the connections properly so that the conversion can be done. So let us see that. So first of all, first step. What is the first step? Get the truth table of the desired flip-flops. The desired flip-flop is D flip-flop. So this is a truth table of desired flip-flop. And excitation table of given flip-flop. What is the given flip-flop here? JK flip-flop is my given flip-flop. So the excitation table of JK flip-flop is this one. Qn plus 1, JK. If Qn is 0, Qn plus 1 is 0, 0, 0, 0 don't care, 0, 1, 1 don't care, 1, 0, don't care 1, 1, 1, don't care 0. Now this is the step 2, right? Now what is the step 3? Append the excitation table of given flip-flop to the truth table of desired flip-flop, right? So now here the desired flip-flop, this is the truth table of desired flip-flop, and this is the excitation table of given flip-flop. Just append them. Okay, so after how to append them, first we need to consider this is the truth table. First we need to write up to this. Then you verify what is the present state and next state. Present state value is 0, 0. What is the excitation? What are the excitations to be given to the JK flip-flop in order to get the combination of present state and next state as 0, 0? That is 0, don't care. Write it here. Okay, now 1, 0. 1, 0, nothing but don't care 1. Next 0, 1. That is 1, don't care. 1, 1, don't care 0. Okay, so this is the conversion table. And from this conversion table, now I want to get the expression for J and K in terms of D and Qn. So now I have drawn the K map here. How many variable K map we require? So only one input and one present state. So 2 variable K map is enough. So this is a K map and this is a value of J and this is the value of K. So once we have got the J and K values, draw the circuit like this. Okay, J is equals to D and K is equals to D bar. As available flip-flop is what? JK. So first draw the JK flip-flop and give the JK input to the JK in terms of D. So like this. So this is now the conversion of JK flip-flop into D flip-flop. So like that you can convert any flip-flop into any other type by following that procedure. Right? Now, construct a mod 5 synchronous counter using flip-flops and implement it. Also draw the timing diagram. So step 1, what is the first step? As I already told you that we have some procedure for designing synchronous counter. So that is find the number of flip-flops required. So as it is a mod 5, so the number of states that it has to undergo is 5 and hence n is equals to 5. And we need to decide the number of flip-flop according to the formula, that is 2 power n greater than or equal to capital N, where capital N is the number of states. So that is how, as a number of states is 5 here. So what is a value of n? So if it is 2, then this is 2 power 2 is 4. Is the 4 is greater than 5? No. So this condition not satisfied. If I take 3, 8 is greater than 5. So that is why we have to take 3 flip-flops. So like that, this condition is satisfied, we need to take choose the number of flip-flops here. So we are taking 3 flip-flops here and choose the type of flip-flop. What is the type of flip-flop? So it is our wish. So here, as it is not mentioned, I can choose any type of flip-flop. So I am preferring this JK flip-flop here. Either you can use D or T flip-flop. And we cannot use SR because it is having some drawback, that is it is having indeterminate state. Limitation of SR flip-flop is it is having indeterminate state. So either you can use JK, D or T flip-flop. So draw the truth table of mod 5 synchronous counter and then get the simplified Boolean functions for the output, the next state, that is the inputs of the flip-flops in terms of the present state, and then write down draw the logic circuit by taking the flip-flops. So this is the procedure. By following this procedure, you can design any type of counter, synchronous counter. Design a counter with the sequence 0, 1, 3, 7, 6, 4, 0 using JK flip-flop. Okay, so here it is having few states, whereas the maximum value that it can measure is 7. So that means what is the number of states I can consider? 8. So that means I require 3 flip-flops. So whereas the remaining states, what are the remaining states? 2, 4, sorry, 4 is also there, 4 is already there. So only 2 and 5. So these are not specified. First let us draw the truth table here. So only the thing is we need to draw the truth table. Once you are able to draw the truth table, you can do the next procedure according to the steps. So you can follow the steps and you can implement any counter, right? So QA, QB, QC, right? So here first state I am considering it as, so let us draw the sequence, that is a state diagram. So if the present state is 0, next state should be 1. If the present state is 1, next state should be 3. Next, if the present state is 3, next state should be 7. Next state should be 7. And if the present state is 7, next state should be 6. And if the present state is 6, next state should be 0. And this is the state diagram, right? It should not be restricted that it should follow the order. So it can follow any order. So that order we have to follow. So if my present state is 0, what should be my next state? That is 0, 0, 1. If my present state is 0, 0, 1, what is my next state? 0, 1, 1. Next, if my present state is 0, 1, 1, instead of going to 4, it will be going to 1, 1, 1. Next, if my present state is 1, 1, 1, next state will be 1, 1, 0. If my present state is 1, 1, 0, next state is 1, 0, 0. Next, if my present state is 1, 0, 0, next state it is going to 0, 0, 0. Right? So this is the sequence it has to follow. So whereas the remaining combinations, what are the remaining combinations? 0, 1, 0, 1, 0, 1. For this, the next state is not specified. So that is why I am taking it as don't care. Now, here he has given JK flip-flop. Consider the JK flip-flop excitation table and derive the characteristic table of that counter, and then get the simplified expression for this that is flip-flop inputs, and then implement the logic circuit using the simplified expressions. Okay. Next, build a 4-bit twisted ring counter using JK flip-flop. Twisted ring counter. So this twisted ring counter is an application of shift register which is operating in serial out mode, right? So if the output, that is Q bar output of the last flip-flop is given as input to the first flip-flop, then such type of counter is said to be Johnson ring counter or else twisted ring counter. So this is the circuit diagram of twisted ring counter and the truth table of twisted ring counter. That is what happens for every clock pulse that is applied. So if my and explain the operation of this twisted ring counter. Consider the initial state as 0, 0, 0, 0, and then apply the clock pulse. Then what happens? So it is 1 now. So as this 1 is pushed here, so now the output of this one will be pushed here. So this output is 0, this output is 0, this output is 0. Whereas this one will become 1, right? So the next state is 1, 0, 0, 0. Now during the next clock pulse, what happens? Again, as it is 0, again this one will be pushed here. So whereas this one is pushed here, so next state will be 1, 1, 0, 0, 1, 1, 1, 0, 1, 1, 1, 1. Okay. Now when all are ones here, okay. So what will be this one? This is 0. This 0 will be pushed here. Okay. So that means now the state becomes 0, 1, 1, 1. So that is what? 0, 1, 1. Next 0, 0, 1, 1. 0, 0, 0, 1. 0, 0, 0. Like that, it is able to count 8 clock pulses. It is able to count 8 clock pulses. As we are designing a 4-bit counter, okay, 4-bit twisted ring counter, it can count 2 into n. That is 8 clock pulses. That is a total number of pulses that it can count with a 4-bit synchronous counter is 16. But it is counting only 8 pulses. So that is n by 2 pulses it can count. So this is a twisted ring counter. Just explain the operation of this by taking one condition. what happens during the clock pulse, each and every clock pulse, and explain this table. And it will be very good if you draw the timing diagram also. Okay, you draw the timing diagram also for this one. I hope it is easy. Now implement modify up and down counter. So that means it has to count up as well as it has to count in decremental order also. So implement this one. So using the synchronous counter design procedure. And then how do you convert a JK flip-flop into T flip-flop? So as we have just discussed the conversion of one flip-flop to the other flip-flop, just follow the procedure and try to convert this JK flip-flop into T flip-flop. So what we need to do, first you have to mention the steps of converting one flip-flop to the other flip-flop. Okay, and follow the steps and then implement the T flip-flop using JK flip-flop. Finally, you get the T flip-flop diagram using JK flip-flop. Here also the same thing. How to write this question? First, write down the steps of designing a synchronous modify counter, and then follow the steps and try to design a modify synchronous up-down counter. Right? Now, explain this. That kind of questions may be asked on critical thinking or problem solving. So whereas now we are coming to the theoretical question or else a long answer question. So explain the design procedure. Most of the question will be a theoretical. Okay. So if you go through the theory classes, you can answer any of these questions from part B. Explain the design procedure of synchronous sequential circuit with an example. So you already know the design steps of synchronous counter. What is that? Just find the number of flip-flops using 2 power. This is not 2n, 2 power n. 2 power n greater than or equal to capital N, where n is the number of small n is the number of flip-flops required. Capital N is the number of states that are to be counted by the counter. Okay, and then choose a type of flip-flop. Draw the truth table of a synchronous counter, and using K-map, derive the flip-flop, reset input functions, and draw the logic circuit diagram. So these are the steps. So example, you can draw any synchronous counter, like a 3-bit synchronous up counter or 3-bit synchronous down counter. Okay, draw the example. Take one example, 3-bit synchronous up counter. Draw the logic circuit, do the procedure, and draw the logic circuit of 3-bit synchronous counter. Now write short notes on shift register. Mention its applications along with serial transfer in 4-bit shift register. Right? So here this is the question. So first of all, write short notes on shift register. Shift register is again a combination of flip-flops in order to store the data. So the number of flip-flops that can be cascaded together depends on the amount of data to be stored. Either it is 8-bit data or 4-bit data, whatever it is. So based on that, you have to choose number of flip-flops. So the shift register, as a name itself indicating shift register, it stores the data by shifting the data from one place to the other place, either in the right direction or left direction. That is either from left to right or from right to left. So we have various types of shift register, that is serial in serial out, serial in parallel out, parallel in serial out, parallel in parallel out. So just draw the circuit diagram of this serial in serial out shift register, 4-bit shift register, and mention some of the applications of shift register. So these are the applications, right? So like that, you can answer this question. First, write what is a shift register, what are the various types of shift register, and then give the circuit diagram of 4-bit serial in shift register, that is SISO shift register, and explain some few points regarding the operation of serial in serial out shift register, and mention the applications of shift register. Okay, so this is about that question. And explain about binary ripple counter. What is a mod counter? So this is one question. Binary ripple counters are also known as asynchronous counter. Just write the definition of asynchronous counter, and you also write what is a mod counter. So mod counter is also called as modulus counter, modulus n counter, which can count n number of pulses. Okay. How do you convert JK flip-flop to SR flip-flop? So as you already know the procedure of conversion, first mention the procedure and follow the steps and try to convert a JK flip-flop into SR flip-flop. So these are all the 3 questions. related to the same topic. So you can again solve these questions in the same fashion. First mention the conversion process and then follow the steps and convert a T flip-flop into SR. Here D flip-flop to JK flip-flop. These are easy, I hope. So you can do it if you know the procedure. Explain the ripple counter design procedure. Ripple counter design procedure means asynchronous counter design procedure. So give the steps and take one example. That also design a decade counter. He has only mentioned decade counter. Decade counter means what? Decade means 10. So the counter which can count 10 pulses. What 10 pulses means? It has to count from 000 to 1001. Right? 10 to 0 to 9. Total 10 pulses it can count. So whereas the remaining states, what are the remaining states? 1010 to 111 or unspecified, right? So take a decade counter, draw its truth table and implement that as a ripple counter, right? Now construct a 3-bit ring counter. Ring counter means, so as I told you that this ring counter and the twisted ring counter are the applications of serial in, serial out shift register, right? So if the Q output of the last flip-flop is given as input to the first flip-flop, then it is said to be ring counter. So mention this point and then draw the 3-bit ring counter, circuit diagram, explain its operation, draw its truth table and timing diagram. Okay, discuss how ring counters differ from twisted ring counter. So here the twisted ring counter can count only n pulses, whereas twisted ring counter can count 2n pulses, 2 into n pulses. So that is a major difference. And one more difference, constructional architectural difference is one, in ring counter Q is connected as input. The Q output of last flip-flop is connected as input to the first flip-flop. Whereas in the twisted ring, Q bar is connected as input to the first flip-flop. Okay. Now explain the JK master slave flip-flop. Give its timing diagram. First define flip-flop and what is a JK master slave JK flip-flop. Before that, what is the limitation of JK flip-flop? We write down it. So what is that? Race around condition is the limitation of JK flip-flop. In order to eliminate that race around condition, we are going for the master slave JK flip-flop. So define master slave JK flip-flop. Draw its circuit diagram. So this is a circuit diagram, that is a logic circuit for the master slave JK flip-flop. Explain its operation and explain how the race around condition is eliminated in this master slave JK flip-flop. And draw its timing diagram showing that the race around condition has been eliminated. Okay, so this is how you can answer this question. So define a JK flip-flop with the help of logic diagram and characteristic table. JK flip-flop. What is JK flip-flop and why we are going for JK flip-flop? That means what are the limitations of SR flip-flop? You mention. If you mention this, it adds to your presentation, right? So you can get good marks. So next, limitations of SR flip-flop and JK flip-flop. Why we are moving to the JK flip-flop and what are the advantages of JK flip-flop? You mention and draw the circuit diagram of JK flip-flop. Explain few points regarding the JK flip-flop and draw its truth table or its characteristic table. This is the characteristic table. And then finally derive the Boolean function for the JK flip-flop. So that is how, this is a truth table and that is the characteristic table. So like that you can answer this question. Now explain the operation of SR and JK flip-flops with functional diagrams and truth tables. Also derive the characteristic equation. As it is asked SR flip-flops, we have two types of SR flip-flop, that is NOR SR flip-flop and NAND SR flip-flop. So these are the two diagrams of NOR and NAND SR flip-flop, and the truth tables will also be different for NOR and NAND SR flip-flop. Just draw the truth table, explain few points regarding the NOR flip-flop, or either of that you can write. Not needed to write both NOR and NAND. It is sufficient if you write either NOR flip-flop or NAND flip-flop. Okay, draw the truth table and then derive the Boolean function. That is how you can answer this question. And even if it will be good if you draw the timing diagram. Even if it is not as, you can draw the timing diagram also. So, Okay. Next, with the help of neat circuit diagram, explain the working of master slave JK flip-flop and also explain how the race around condition is eliminated in it. So first you write down the race around condition, same fashion as we have, just now we have discussed about master slave JK flip-flop. Same fashion you can answer the question. So just show the race around condition with the timing diagram. So this is a race around condition and this can be eliminated using master slave JK flip-flop. Draw the circuit diagram of master slave JK flip-flop, explain its operation and draw its timing diagram such that showing it is eliminating the race around condition. Right? Now explain the operation of D and T flip-flops with functional diagrams and truth table. Also derive its characteristic equation. So draw the truth table, diagram and the timing diagram if possible and get the Boolean functions for this. Next, explain with suitable logic timing diagram, serial in serial out, logic and timing diagram, serial in serial out shift register, parallel in parallel out shift register. Okay, unidirectional shift register. So this is a serial in serial out shift register. Just draw the circuit diagram, explain its operation, give its truth table and also the timing diagram. So this is a timing diagram. Now parallel in parallel out, explain how the shift register operates in parallel out mode. So how the inputs are applied parallelly and the outputs are read parallelly, and then give its truth table and even timing diagram. Now explain with neat diagram the truth table 4-bit SIPO, that is serial in parallel out shift register, to store 1011. So you draw the parallel in serial in parallel out shift register logic circuit like this, give its truth table and explain few points, and in order to store this, how many clock pulses are required, that you have to mention. So step by, for each and every clock I want to load this, what is happening in the register, you just write on that. So that is how you can answer this question. And with neat logic circuit, explain the different modes of operation of universal shift register. First, define universal shift register. Why it is so called? Because we can shift the data, that is either from left to the right or right to left, and even we can also perform serial in parallel out or parallel in parallel out operation. So that is why we can call this as universal shift register. Okay, so this is the circuit diagram. Explain few points. What happens if the selection input is 00, 01, 10, 11, how the data is shifting to the left or shifted to the right, and how parallel loading is done. Just mention all the points so that you can get the full marks here. Now, with the help of schematic diagram, explain how a serial shift register can be transformed into ring counter and Johnson ring counter. So this we have already discussed, ring counter and Johnson ring counter. So it is an application of serial in serial out shift register. Just draw the serial in serial out shift register and connect the output or Q output of last flip-flop to the first flip-flop input. So it will be converted into ring counter. Johnson ring counter. So Q bar will be connected as. So explain some few points about the operation of ring counter. Give its truth table and timing diagram. And also Johnson ring counter from the serial in serial out shift register. Give its truth table, timing diagram and all. So this kind of questions may be asked from the sequential circuits fundamentals, and I hope you can answer any kind of question that can be asked from this module 5. And if you have still any doubts, so you can go through the lectures that are available on problem solving, on counters, and also theoretical concepts on flip-flops, counters and shift registers, so that you can get a clear-cut idea to answer any kind of question asked on module 5, asked from module 5. That's all for this lecture. I hope it is clear to you all. Thank you everyone.
Like, share and subscribe. Hit the bell icon for more updates.